So it is my pleasure and honor to introduce Professor Christos Georgakis. He comes from Stanford University, where he is the professor of chemical and biological engineering. He is also the Bernard Gordon Senior Faculty in Systems Engineering. He received his bachelor's back in Greece in National Technical University. After that, he moved to Illinois for master's and Minnesota for the PhD. That generation, we had a few actually, we were discussing this as that generation of chemical engineers that Minnesota produced in that time frame, so definitely younger, ended up becoming professors in many American universities. After that, he became assistant and associate professor at MIT. At the same time, he initiated the Chemical Process Engineering Research Institute in Greece. That's important because this is where I did my PhD, many years after they initiated it. And after that, he moved to Lehigh, and now he's with Tufts. He's the winner of the Dreyfus Foundation Award and also the CAS division of the computing award of the CAS division of the AACT. Today, I actually know Christos for his work on design and control and how you design processes taking into consideration the control many years ago when I was a student. But today he's going to discuss on data-driven modeling through methodological generalization. So with that, I would like to ask Christos to start his presentation. Thank you.
Christos, if you don't mind, can you add two logistical things? So I'll circulate this attendance sheet. If you can just sign in your name and your contact information. And also, there are feedback forms on your chairs. Please fill in those feedback forms for our future improvement use. Thank you, Christos.
From looking at the audience, I suspect a lot of you are graduate students. Right. One of my rules is that I'm not going to take any questions from the faculty until I have 4 questions from the students. So be prepared, because I'm going to insist on that. And thank you for coming. I think that traditionally I've been working on process dynamics and control from the chemical engineering perspective, which is a much more difficult perspective than the perspective for mechanical or electrical or aerospace engineers. You realize that. The perspective, the difficulty is that when you make sophisticated dynamics and control systems for an airplane, you can amortize the cost of that development over several copies of airplanes that you sell. Or if you do it for a very expensive car, you can amortize the cost of an expensive control system for a Mercedes-Benz or a Chevy automobile over several copies of the car. We chemical engineers are much more constrained in that when we study the dynamics and control of a given plant, all chemical plants are one of a kind. You never make 2 or 3 identical plants. You're not going to make them in the same location. You're going to make them in different parts of the world. They're going to be different resources that you're going to utilize, different markets. So that makes the economical challenge on process control much more difficult. And even if you do not worry, and even further, an additional difficulty is introduced when you want to control batch processes as opposed to continuous processes. When you want to control continuous processes, processes that make gasoline, refineries, processes that make polymers, processes that they make large commodity chemicals like ammonia and so forth, the production amount that you make is quite high, and thus an improvement of a few cents per pound is a lot of savings, and thus the control can be motivated quite substantially. And in general, for these type of processes, you will spend the time to develop what I usually call knowledge-driven models, trying to understand the inner workings of the process, trying to write, some people call them fundamental models, trying to write, in our case, the material and energy balances, both steady state and dynamic, and so forth. And by the way, how many of you are chemical engineers in the audience? Okay, a minority, proud minority. Now, when I joined TAFS, for many years at Lehigh University, I had an industry university cooperative research center in process model and control, and many of the companies we're sponsoring were the usual big chemical companies, the Exxons and the DuPonts, and a lot of international companies. When I moved into TAFS, I became more interested in taking up an additional challenge, that of worrying about pharmaceutical processes. And of course, in pharmaceutical processes, most of the products are being made in batch. And batch processes, and the production rate is much smaller, so the motivation for developing knowledge-driven models is even weaker. And for this reason, to some extent, I switched my interest and tried to develop data-driven models. And I will explain to you what. Now, for the benefit of the audience, how many of you do know what a batch process is compared to a continuous process? Okay, the chemical industry know, the others don't. Having a refinery and feeding it crude oil day and night, all days of the week, and getting gasoline, fuel oil, that's a continuous process. One might say McDonald's is a continuous process, right? You know, but having a fine risotto made, fine food, is almost a batch process. Batch process is what you do every night when you cook at home, right? You just make one of a kind. Next day will be a different type and of course, in some cases, you might end up be interested in cooking a leg of lamb, and that could be a batch process. You are not going to develop a heat transfer model and a chemical model, or what happens inside the leg of the lamb, in order to optimize the conditions. You're going to do experiments. Okay? And in many circumstances and in many industrial applications, people do design experiments. And the design of experiments, and I'm going to talk to you about the methodology of design of experiments and two generalizations that we have introduced in order to make it more applicable to a whole new set of circumstances, especially for batch pharmaceutical processes, although it has applicability to other processes as well. So we're going to generalize the design of experiments by designing dynamic experiments, and we're going to generalize the type of models derived from this type of experiments by developing dynamic response surface models instead of response surface models. And we're going to use them for processes that they're not well understood. And we're going to try to use these models in order to optimize such processes, and in some cases, as I will say, to understand their knowledge, to understand the inner workings and develop knowledge-driven models. And I'm also going to talk to you about some industrial applications.
What's KNM?
Knowledge-driven model.
KNM. Your KNM is
No. Okay, it's misspelled. KDM, knowledge-driven model, sorry. DoE, design of dynamic experiments, in essence is a field of applied statistics. It applies into every engineering field. It aims to help you design the experiments in such a way so that you can get the maximum amount of information of what happens in your process with the minimum number of experiments. And as such, there are techniques like analysis of variance to tell you how to develop interpolative linear and nonlinear models in order to describe the cause and effect relationship between the conditions and the results that you are going to derive. And let's skip that silly batch process. It's not silly, it's an important batch process, cooking a leg of lamb. In order to find the best conditions in order to cook a leg of lamb, you are going to buy small and large legs of lamb. You're going to buy lamb from Utah, from Greece, from New Zealand, from Australia, just in case that makes a difference. You're going to cook it for a shorter time, a longer time. You're going to put more salt, more pepper, less pepper, and you're going to determine the temperature at which you want to cook. In order to find what is the optimum recipe, you have to do quite a few. You have to change these conditions, cook the leg of lamb, maybe have a panel of 5 people who are going to give it a grade of 1 to 10, and then you're going to develop some sort of a model that tells you which conditions are going to be the most appropriate. And as you can see, depending on the number of factors that you have to change, of course in a chemical reaction you might change the composition of the reacting material, you might change the temperature at which you operate. You can imagine not only chemical engineering processes but other processes for which you might do these experiments. You want to minimize the number of effort, right? How many sizes of leg of lamb are you going to do? How many amounts of salt are you going to try? How many temperatures? How many cooking times in order to develop some understanding of what... So one of the conditions is that the design of experiments has a limitation in that the inputs are time invariant inputs, do not change with time. And thus if I'm going to use the traditional method of cooking a leg of lamb, I'm going to limit myself into cooking at a constant temperature. Now, of course, I know the ovens that you have at home do not have sophisticated controllers to control the temperature profile. They only operate at a single temperature, but who said that we should not try time-varying temperature profiles for getting the best leg of lamb cooked? My theory is that you first have to raise the temperature, burn the outside of the leg of lamb, seal the juices, and then slowly cook it for some time. What is the optimum temperature increase? What is the optimum temperature decrease later on? Or what time of period? And something similar could happen when you have a bioreactor, which you have to feed with some sugar source in order to make, let's say, penicillin. How much sugar source you're going to put initially, how much you're going to put later on. The input profile is a time-varying profile. So there is a need to generalize in that aspect. Also, the output measurements of the classical design of experiments techniques usually were taken at the end of the experiment. So let's say that we're going to operate a certain batch reactor to make a certain new pharmaceutical. We're only going to measure the compositions, what happens at the end of the fermentation or the classical chemical reaction, or are we going to measure compositions throughout the batch? And nowadays it's much more easy to measure compositions throughout the batch, either by robotic reactors where they take a sample and they put in a gas chromatograph, you get the results, or even by spectroscopic measurements, IR, Raman, whatever you have, in order to have a composition, a measurement of how the compositions change with time. So in that case, the measurements will be time evolving, and thus our answer will be the generalization on the input, design of dynamic experiments, the generalization on the output, design, dynamic response surface models. So here is the temperature profile of the oven in cooking a leg of lamb. You might say, okay, I want to operate the temperature in this domain. Let's say that this red line is my mother's cooking profile and this blue line is my grandmother's cooking profile, and I think that the optimum is somewhere in between. One recipe gives you an overburned leg of lamb, the other gives you an undercooked leg of lamb, so to speak. So the first thing that you have to design in a time-varying input, U of t is the domain in which you're going to do the experiments. The blue and the red line, in essence, and the yellow one is the middle of the two, is your definition of the domain in which you want to do the experiments, and of course that's a preliminary first guess where you want to operate. When you do that, then you define a dimensionless input variable, z of t. Usually this is called a coded variable, which in essence is the fractional change from the middle. The advantage is that with this new design variable, this varies between plus and minus 1. And often we are going to describe the temperature as the fractional temperature from the beginning to the end of the experiment. In this first simple case, I'm going to consider the experiment to be of a fixed duration, but we can also consider. And the main contribution and the main generalization of the method comes here in describing this time-varying function, which is function of time, which is infinitely dimensional, in terms of a finite expansion in terms of shifted Lausanne polynomials, and thus the unknowns about the cooking profile for our leg of lamb, so to speak, are these coefficients x1, x2, x3, because you're going to use only a finite number of coefficients because you're going to do a finite number of experiments. You cannot do too many experiments. So for example, if you were to only consider linear changes of the temperature of the oven, you're going to have these 9 possible profiles, constant and at the top value, constant at the middle value, constant at the bottom value, and linear from the top to the bottom, from the top to the middle, and so forth. The coefficients x1 and x2 are to some extent constrained by these inequalities, and in essence are in these diamond shape between plus and minus 1. So you're going to do possibly these 9 experiments. Now, of course, if the experiments will be done in this curved domain, these linear profiles become curved, but in any case, these are the 9 temperature profiles in our cooking of the leg of lamb type of experiment. If you want to have more granularity and more detail, and you want to describe the time-varying profiles with 3 shifted Lausanne polynomials, then you have 3 x1, x2, x3 factors, variables, coefficients to define each of the experiments, and here you have a set of a larger number of experiments if you want to go into such additional detail. So in general, you design the experiments, you collect the data, you perform a multilinear regression. The models are non-linear, but the parameters are linear. And then you develop what's called the response surface model, and then you can do whatever you want to do. You can mostly use it in order to optimize and find what are the conditions of, again, the cooking of the leg of lamb, so that the panel will give it the highest score. And the response surface model that you do, because it is interpolative, it's mostly a polynomial form, and usually it stops with quadratic terms. You can put additional terms, cubic, 4th order, 5th order, but then the coefficients beta 0, beta I, beta ij that you have to estimate increase in number, and thus the number of experiments that you have to do increase in number, and usually people will stop with quadratic. When we do design of dynamic experiments, the approach is the same. The only thing is that now we have time-varying inputs that are expressed in terms of the shifted Lausanne polynomials, and that we have this, what we call dynamic subfactors. So again, parameterize the time-varying input, do the experiments, develop the response surface model like this one, and then optimize. Let's do some examples now. And I apologize, these examples will be chemical engineering examples, but very simple. Here we have a simple reaction of A1 going to A2. So it's a simple chemical transformation, the simplest that you could imagine. The rate at which it moves to the right is given by K1. The rate that removes to the back is by K2. And in order to, let's fix the duration of the experiment to 2 hours. And let us do what we'll call a model-based optimization. Let's pretend these calculations are calculations, quote-unquote, in silico, where the process is simulated with the left-hand side, and now the right-hand side is going to try to optimize. Now, in the first instance, the right-hand side knows exactly what the process is. We're going to use the model. There is no model mismatch between the model that will be used in the optimization and the simulations. And we can calculate that the conversion to the desired product A2 is a little bit less than 75%. That is if we know everything about the process and we utilize the model. And the optimum temperature profile, which has been constrained between 15 and 50 degrees C, is to keep it at 50 and then to gradually decrease it. At least for this specific reaction in which the activation energy of the return reaction is higher than the activation energy of the forward reaction. And let's keep it at that. The chemical engineers might infer something else, but if the activation energy were different, the character of the optimum would have been different. But anyhow, if we have full knowledge of the process, we do what I call a model-based optimum, and this is the maximum conversion that you can achieve in 2 hours, and this is the temperature. Constrained by the top and then gradually decreased. Now we're going to do 2 other experiments, in which experiments, the right-hand side who does the experiments does not know the details of the model, right? The kinetics are known, the inner workings of the process are unknown, and we're going to do experiments, and we're going to try to find experimentally, not by knowing what's happening inside, how close we can come to this number. We certainly cannot come close. We cannot do better because you cannot do better with ignorance, right? The question is how close we can come. So we do a DOE, classical DOE. Single factor is the reactor temperature, but in this case the temperature has to be constant with time. I'm going to do one experiment at the lowest temperature, one experiment at the highest temperature, and 3 experiments at the middle temperature. You need to do 3 in the experimental setting because you're not going to get the same results by the repeated experiments. The process will have some variability, and that variability you need to take into account when you do your statistical analysis. In DoDE, we're going to do linear profiles. So we're going to do the 9 experiments that I showed you before, where the temperature linearly changes from the maximum to the minimum. And here are the results. The DOE optimum at a middle temperature of 36 degrees, which is between 15 and 50, gives you a conversion of 71%. A little bit far away from the 74%. 3% is substantial. But the DOE optimum is just a little bit lower than this. And by a linear temperature profile between 50 and 28, you really can come as close to the true optimum without needing to know the chemical kinetics. So for example, if you were to come to me and say I have a pharmaceutical reaction, optimize it, you have 2 choices: to spend a lot of time learning the inside kinetics, and I can do a few experiments, and maybe I can optimize it quite expediently for you. I'm not going to help you understand the inner workings, but that will be quite useful to optimize it. Now, if I have a more complex set of reactions in which I react A and B to make the desired product C, But in this case, the co-reactant B decides that instead of making what is desired C, you will make a byproduct. And for this reason, you're not going to put all of B inside the reactor. At the beginning of the reaction, you're going to be feeding it. And the decision variable is how much are you going to feed and what would be the feeding profile. Here are the experiments that we have done. And here we have also varied the duration of the experiment from 1 hour to 1.5 and half an hour. We did the experiments. We collected the amount of C that was produced in each one of those experiments. We do not know the inner workings of the process. We developed the response surface model. And if you want to maximize the amount of C made at the end of the reaction, this is the optimum feeding profile, and the experiment would last close to 1.2, let's say, hours. But in many circumstances, you might not want to optimize the amount of C that you make, but you might want to optimize the amount of product that you make per unit time, because maybe I waited for too long to get a few more grams of the desired product. I could have stopped the reaction and start afresh, and at the end of the day, I will make more product by having more than one reaction. So in this case, you optimize the same model, and here is the quite different input profile of the co-reactant B. We also did some experiments in a pharmaceutical company a few years back. The pharmaceutical company, which is in the corner of the Turnpike and 495, probably about 30 miles west of Boston. Used to be called Sepracor, was then bought by a Japanese company, now it's called Sunovion. Sunovion, they tell me, is the mixture of sun, which is of course the symbol of Japan and innovation, so Sunovion. They are very expert wordsmith when it comes to deciding what is the name of the company. This company wants to have a reactant, an expensive catalyst, and wants to produce one of the two diastereomers. This is trans and the cis product, they're mirror images of each other. One is pharmaceutical uses, the other is an undesired one. You don't want to produce much of it. The catalyst is expensive, and what we want to do is maybe we had a simple profit equation here, incorporating the value of the product and the cost of the reactants. It's an approximate one. And what we wanted to do is to learn how would you operate this reaction so that you can maximize the amount of profit. Right? What you want to do is you want to convert as much of the reactant to the desired product, but you want to have a maximum small amount of the undesired product. We did experiments, and I'm not going to bother you with all the details. And then we did the following type of experiments. We changed several other things, and I will explain to you the classical DOE factors, but with respect to temperature, we did dynamic experiments because we thought that varying the temperature with time would be beneficial. So we only varied the temperature with time linearly, and we only did these 4 experiments mostly because, well, we wanted to minimize the number of experiments. However, we also considered different durations of the experiment, this being 3 hours and this being 4 hours, but in all cases, the time variation of the temperature was linear. We did a set of classical experiments called DOE experiments, in which we varied the temperature, constant with time. -1 is the minimum value, +1 is the maximum value. Here is something related to the excess of reactant. We put more reactant that can be dissolved in the solvent. Here is the catalyst amount, and if it is -1 is the smallest amount, if it is +1, the largest amount of the catalyst. Here is the batch time, and there are two performance criteria, and of course something that relates into dollar values. We want to maximize actually this value, but we want to keep the selectivity to the desired product above 95%. If it is above 95%, we don't make too much of the unwanted product. And this is the money that you can make, if you will. This is the 7th run, which is the best. The selectivity is above 95%, and this is the best conditions. You could have made more money here, but the selectivity is less than 95%, and the product is not sellable. When we do design of dynamic experiments and we vary the temperature linearly, the best run was number 9, and we made that much money, if you wish, and the temperature was a decrease in temperature. -1 is characterizing the slope of the temperature with time. And of course the difference was about 48%. Now in this case we also tried to develop what I will call a knowledge-driven model, a model that characterizes the details of the reaction, the details of the thermodynamics. But unfortunately we had to have another PhD thesis to do it, and thus in this case we proved expediently that if you're pressed with time, the design of dynamic experiments can help you quite a bit.
So you're constrained to just selecting one of the results. You can't interpolate or extrapolate?
I could, for the sake of simplicity, we're just comparing. You could take the model and you can optimize an intermediate solution, and indeed we did. But for the sake of minimizing the number of slides that I'll give you, yes, you could. Here's another case. Here's a model that, again, we're going to use it in silico. This is a model that describes the penicillin fermentation, a model that was developed in the 80s. The balance, the volume inside the reactor is you start the bioreaction and you put some materials in it, and then you feed additional sugar source. And the decision is whether you're going to have enough and what will be the optimum feeding profile for the sugar source. This is the balance for making the biomass, the cells that will produce penicillin. This is the sugar source inside the reactor, the substrate, and this is the penicillin concentration. So we're using this model in silico, and we are developing design of dynamic experiments in which we vary the batch time and the initial biomass in the reactor, and of course the feeding profile of the sugar source. To our biggest surprise, we are getting 85 grams at the end of the batch. And if you were to use the model that describes, that simulates the process into a model-based optimization, perfect model process match, you get slightly higher than that. To tell you the truth, we were quite surprised how closely we can come to the best optimization results by doing a set of experiments. So what I told you so far is that in the design of experiments, I presented to you the first generalization in having dynamic experiments. So if you have an experiment and you don't know how to characterize the process, you're going to do experiments. What I'm telling you now, you could do experiments utilizing time-varying inputs. In this case, in the last case, was the feeding profile of the sugar source for the fermentation. In the cooking of a leg of lamb was the temperature profile inside the oven, right? I'm starting a company that will give you ovens where you can describe with shifted Legendre polynomials the temperature profile of cooking. I'm not serious. So now we're going to go on the other side, and we're going to say we are going to have measurements, and again with a reacting process, a reaction. Think of it now, and there is a case in which I collaborated with some people at Pfizer. They have a new pharmaceutical they're concerned. They made several experiments. They want to find the conditions where they can maximize the number, the grammomoles of the desired product, but at the same time they want to minimize the grammomoles of the byproducts because they could be poisonous, they could have adverse medical reactions. So we're going to have time-resolved measurements. The classical model, let's say that you do a chemical experiment and you measure every hour for 12 hours. In principle, you could develop such a model for each of the samples that you took. So a model for what happens after 1 hour, another model for what happens after 2 hours, another model what happens after 12 hours. That's not nice. That's not very convenient. That's not. So in this case, we are generalizing this, and instead of estimating these coefficients beta, we're going to estimate functions that vary with time. So in essence, this is the generalization of the response surface model to a dynamic response surface model when the measurements, when the model coefficients are not coefficients, but they're functions of time. And we're going to estimate these functions by taking measurements of the output y at different time instances. Again, we express these unknown functions in terms of the shifted-Pleasant polynomials, and if you are not in love with shifted-Pleasant polynomials, I recommend that you do become. These are polynomials. So if you don't want to think of them as polynomials, just think of them as t squared, t cubed, powers of time. The advantage of the shifted-Pleasant polynomials that in the interval between 0 and 1, they're orthogonal. And that is quite mathematically convenient to work with orthogonal functions. You'll have a number of parameters gamma. Of course, the parameters gamma will be fewer than the number of measurements k that you have at each batch. And here is an example back in our simple A goes to B reaction. Here we're going to measure at the beginning, the end, and in the middle. We're going to have 3 measurements. We're going to estimate the profile with a second-order polynomial. It's not going to be very accurate, right? So don't expect that you're going to do that with only 3 measurements during time. In order to assess in a statistical, exact way how accurate the models are, we develop a certain number of criteria and a hypothesis test. Primarily, when you fit the model, you want to minimize the sum of squares that the model does not represent, and this statistical test trying to see whether this sum of squares is comparable in value with the normal variability of the process. And then there is an F-test that one can do. And here are the results. For example, let's say that we're going to measure for this simple A to B reaction at 9 time instances. The F-test says that if I have 5 shifted-Pleasant polynomials to describe the profile, I am on the green line, which is an acceptable and accurate enough model. So in essence, I can live with 8 and 5th interpolating polynomials. I can live with 6 and 5 interpolating polynomials. The green squares are where the model is accurate enough. Here is one of the comparisons of what the 2 experiment gave, the simulated profile, but to that experiment I have not added the plus or minus points due to the uncertainty of the measurement, and the estimated profile is the red one. We've done it for this more complex reaction, a similar table tells us the number of polynomials that are sufficient. Here are some of the profiles. They are quite accurate. Here I want to compare these two cases for a second, if you wish. Here I have 10 measurements from the beginning to the end of the experiment. And I have 10 measurements here, the same number of measurements. Here I'm using 5 polynomials. Here I'm letting the model to use 9 polynomials. The model are identical. Thus, having more polynomials does not incorporate a more detailed model. And this is primarily due to how we estimate our parameters in the model by using not just least squares regression, but stepwise regression, which tests the significance of the model parameters, and if they're not significant, it throws them out of the model. The same with the penicillin concentrations. You can see that even when the profile has discontinuities in the derivative, we can approximate it quite effectively. So now, let us go back into this reaction. Keep in mind, the reaction is that we are putting all of our A initially in the reactor, B is fed in semi-batch form, C is the desired product, and we want to minimize the undesired product. This diagram here, chemists and chemical engineers call it the stoichiometry of the reaction. If you have a completely new, let's say, pharmaceutical reaction, you might not necessarily know the stoichiometry of the reaction. Or you might know the main reaction because, yes, you know what you put in A and B and you know what you want, but you might not know what are the additional reactions happening there which are not desired and produce byproducts. With the design dynamic response surface methodology, I can now calculate a model how the concentration of the reactant A, how the concentration of the reactant B, how the concentration of the product C and the byproducts change with time, not for one experiment, but for all my experiments, because depending on what experiment you did, these the values of the xi's will be different. For all the experiments that you could possibly run in the space that you have selected to operate. In essence, I smoothen the composition measurements into profiles, eliminating a lot of random errors in these polynomial descriptions. And I can take these polynomial descriptions now and can differentiate them. If I differentiate them with time, in essence, I calculate the rate of appearance and disappearance of the different species. And I can plot them, and you can see these are very smooth plots. You can see that the blue line is the rate of disappearance, because it is negative, it is disappearing, of the reactant A. Of course, the reactant A will disappear. The rate of disappearance of the co-reactant B, of course, it is like this. The rate of appearance of the desired product C is positive, but then later on it becomes a disappearance because it transforms itself into the byproducts. And obviously, in this case, you should never run the reaction beyond this time instant. Okay, that was experiment 1. So in essence, now that I have calculated functions of the rate of appearance and disappearance, and I can put this rate of appearance and disappearance in matrix form This is for the kth experiment, the rate of appearance of the reactant A at the beginning and at several instances in that experiment, for B, for C, for D, and for E, and I can put them all together into a big matrix for all experiments. Here I'm doing something important, because for a new reaction you would not know the stoichiometry. You would not know which molecule would kiss which molecule to make a new molecule. And you would like to take this data and test different stoichiometries. So in this matrix, which is 9 experiments and 5 species, the matrix is 909 times 5, I will do singular value decomposition. How many of you know what singular value decomposition is? Not that many. But many of you know what eigenvalue decomposition is, right? Eigenvalues and eigenvectors, you calculate square matrices, singular value decompositions, think of it. Not exactly, but it's almost the same. Do eigenvalue and eigenvector decomposition for non-square matrices. Now this matrix has 2 different dimensions. It has columns, there are 5, and rows, there are 909. The rows express changes with time. The columns changes due to the interaction of the molecules. And if you calculate the singular vectors, if you calculate the singular values, the significant singular values, that number, well, I don't want to say it's a magic number, tells you how many reactions are taking place. In this case, there are only 3. So if you were to take this data and calculate only 3 of the singular values given in the matrix S are going to be non-zero, or at least significantly non-zero. Okay? The singular value decomposition breaks the matrix into what's called a left unitary matrix and a right unitary matrix. This left unitary matrix, to some extent, is the key to what happens with time. The right unitary matrix tells you what happens among the species. So for example, if I have 3 singular values, I only keep only 3 of the 5 right-hand side singular vectors, and here they are written in row form. This fellow has a unit length of 1, this fellow has a length of 1, this fellow has a length of 1, and they're orthogonal with each other. So, something that possibly only the chemical engineers might fully understand is that by any chemical reaction that takes place in here, any stoichiometry, here is a stoichiometric vector that says -1 for the A species, it is a reactant, -1 for the B species, it's a reactant, +1 for the C species is a product. Okay? So this is the representation, the matrix representation of this reaction here. Take this A, B, and C and put them on the other hand side, and of course the signs are going to change. This is the vector that you're going to get. The question is this reaction supported by this data? And in order to do that, in essence, you have to take this reaction and project it into the subspace that these 3 vectors represent by this matrix calculation. And if the reaction comes out to be identical to what you started with, then the reaction is supported by the data. And in this case, we've developed some score that if it is close to 100, and we tried the 3 reactions, which are the true reactions. Of course, in this case, we are slightly cheating because we know what we put in the simulation, and we know what we're testing. So this is Well, it's not sitting, you're testing your ideas. So this one projects perfectly well. Keep in mind that the second reaction has a -2 because 2 molecules of B react to give you the molecule of D. In case you did not know that and you put -1 in here, the test is not going to succeed. Okay? So of course, this was not a fair test of the methodology because I knew what I used to simulate, but first you have to learn how to crawl before you run. Last Christmas time, I was working on some data that Pfizer people gave me in which they had done 17 experiments, not 9. They measured the composition. Actually, they didn't do the experiments. They were doing the simulation themselves, right? And they're just giving me compositions, and I did not know what was the reaction that they did. So I developed similar models, and when it came to test the reactions, they gave me 15 possible reactions. Some of which were the true reactions that they used in the simulation, and there were 8 that they used, and some others that they changed just to see whether, well, none of the wrong ones tested positively. 6 of the 8 true ones tested positively. The 2 that I failed to do, most likely there were reactions that happened in small amounts, and the results were to some extent scattered or covered by the measurement error that they had introduced. So to some extent, we feel very positive about it. This methodology does not need you to measure all the species involved. If in this case you measured A, B, C, D, but not E, one of these bioproducts, just because you were not aware of it, then you only involve 4 species. The corresponding 3 singular vectors will be 4 by 3. The test now will miss the species E. You see that in the last reaction, I know that C is a product, but we don't know what it makes because we're not measuring it. The test is equally successful when the numbers are correct and equally unsuccessful when I modify one of the numbers. Here in reality, you don't need to have the full set of reactions to test. You can test one reaction at a time, and thus it's a much easier test. And of course, if you don't have candidate reactions, but if you know that the stoichiometry varies, usually will vary between +2 and -2, you can do a combinatorial testing of the different reactions in order to discover what. Now, if you have the right stoichiometry, then you can take the data for the rate of change of each species, the rate of disappearance of A, the rate of disappearance of B, the rate of appearance of C, D, and E, and then you can calculate the rate of reaction. Each reaction, in essence, is an avenue in the composition space, and in this case, we have 5 components. We are working on a 5-dimensional space, and there are only 3 avenues in which the species are changing. We can calculate the rate of change in each of these experiments, and as you can see that they are representing here for each of the, in this case we had 9 experiments, so I'm representing them, 3 of them here. And now that if you have the rate of change of the reaction and the corresponding species concentrations, you can estimate how one relates to the other, because that's the chemical law that describes how a rate of change of a reaction. So what did I tell you now? In this segment, I just told you that we took the response surface model of the classical design of experiments and we generalized it into a dynamic response surface model which utilizes time result measurement. So I described both generalizations, and I'm going to give you some quickly with not much details, so my time is limited. some applications. I'm going to give you just a bird's eye view on an application that we did with DoW on a batch polymerization reactor. I told you a little bit about the Pfizer test that we did involving 10 species. And then we've done some other things about utilizing such type of models for moving and optimizing the transition of a continuous process from one operating point to another operating point, switching from polymer 1 to polymer 2 production. But I'm going to give you a little bit about what we did with DoW in the last year and a half. DoW was interested in the design of dynamic experiments, and of course they would like to apply it into both pilot or semi-pilot or even industrial processes, especially let's say that you have a process, and this was the case here, in which they make a polymer. Let's say that you have a plant, and actually, even though this testing that we did with the methodology was done in silico, they had a detailed model of this polymerization process. They did not do the real experiment. That's the next phase. They didn't tell me what the polymerization process is. It's a batch polymerization process. Again, they start the reactor, they put things in, they make a polymer, empty it, make another one. Okay. So here, the constraints that they told me. The fixed amount of monomer is that much. Don't use less, don't use more. The reference operation lasts 1 unit of time, and I don't know whether that's minutes, hours, weeks, because they made their numbers dimensionless for proprietary reasons. The product that I make, or they make, needs to have less than 1% impurities and needs to have only 1% unreacted monomer in order to be an acceptable product. The reactor temperature could be between these two extremes. Again, this is not in C or in F, degrees F, it's dimensionless. And the monomer flow rate needs to be between 0 and some maximum value. The issue, of course, here is, and I have to avoid increasing the adiabatic temperature above 1.7. That's a safety constraint, and there is certain maximum cooling capacity. The polymerization reaction exothermic, you have to control the temperature of the reactor by providing quite a bit of cooling. So, they said, prove to us that your design of dynamic experiments is worth, has potential here. Design, modify the temperature and modify the feeding profile of the monomer with time as you wish, and tell us how to operate the reactor so that we minimize the batch time. Imagine that you have a plant that makes this polymer, right? And customers want to buy it. And you're producing the polymer in the maximum amount you can, and you still cannot satisfy the customers. What choice you have? Build another plant, right? Or if you decrease the batch time that it takes to make the same product, then you increase productivity. So that was the objective here. Decrease the batch time, but make the same quality of polymer. So they said, change the temperature as you wish. Change the monomer feeding flow rate. Can you make the reactor finish the polymerization in less time than 1 day, 1 hour? Okay? I know nothing of the inner workings of the process. I I don't know what polymerization is. I don't know any kinetics. I don't know any thermodynamics of it. I am almost blindfolded, right? They only gave me 3 process runs in which they gave me the feeding profile of the monomer, the temperature profile, which is constant with time, the adiabatic temperature rise, the incoming temperature of the coolant, the outgoing temperature of the coolant. One of them made good product, the other 2 did not make good product. So they say, go. Design the experiments, and we'll give you the results. Again, they were not doing it in the experiment. They were not trusting me to go and do that in the real experiment, in the real plant, right? They were doing it for this specific product. They had developed a very detailed model which they indeed used to optimize this process. And they were trying to see whether my methodology will be worth anything as far as optimization is concerned. So what I do, I design preliminary set of experiments. My objective now is to reduce the batch time, so I am slightly reducing the batch time only by 6.5%. I'm not going to go reduce the batch time in half, right? I mean, you cannot just jump off the cliff in one step. You have to go gingerly and slowly. I have to change the process a bit, ask them to do the experiments, measure the product characteristics, so I can collect data and develop an interpolative data-driven model that I can use to do the next. So then they do the experiments. As I said, they do it in silico. Then they give me the results. I develop a model. I optimize. I define a new set of experiments. And as I have some understanding about the cause and effect of the temperature profile and the monomer profile, what are the impact on the quality of the product, what is the impact on the unreacted monomer. So at the end, and I'm not giving you a lot of, I'm giving you, do I have a few minutes?
-10.
Anyhow, I can go very quickly. This